So this is this camera.
Oh, cool.
And so what you can do in order to show this, you have to pin this one.
What's that?
You can pin this one.
Pin it?
No, let me show you that. Yeah.
You're right. I got an A, and then the second semester, like it went 2 rows, and I redesigned my first project. And then Amal was like, "I can't do that." He was like, "I didn't approve it," but I was talking to him about.
So,
How's that? Is that the right angle? Maybe
I see yourself. Yeah, this is what we see. This is what.
okay, I can.
Yeah.
This is your big.
And if you want, maybe I can face this towards you. Is it better?
Yeah, it's better than that.
Okay. Okay, so if you maybe stop sharing for a moment, I'll introduce you. Share this. Is that fine?
Oh, okay, I just went like this.
No, no. I want to show it off. That's fine. You can just explain.
You want to show it? Yeah, that's fine. I'll stop sharing it.
Yeah, excellent. Okay. Good morning, everyone, and welcome to this seminar. It's a seminar presented by friends from Mathworks and being held at San Francisco State University. And thank you, everyone attending. And I especially thank the presenter, Dr. Let me make sure that I pronounce name correctly, Denry, Dr. Terry Denry, who has presented for us a couple of times. And his colleagues are here, so I welcome them as well. We have a faculty member, Dr. Quintero, which I appreciate him coming, and all of the students from different classes. Basically, what we have here, we have students from System Dynamics, Engineering 205 to what else? Control class, I can see, and some other students. So we have had some sessions before with Mathworks, and our students enjoyed the interaction with them. They are using different toolboxes in different courses. We are using Simscape, control toolboxes, Simulink heavily, and for hardware in the mechatronics, we are using the Simulink with the hardware. And today, this excellent seminar is going to show us how to work with Simulink Mathworks with the hardware, do the control, and do the system dynamics as well. So it's a combination of all these materials. So we are excited to hear from Terry, and thank you so much, Terry.
All right, thanks, Mataba. Yeah, Mataba and I met, what, about 3 years ago, something like. Mechanical part. And I like that because I think all your loads, and the thing it really does is some sort of mechanical thing. It's the mission, the creative part, I believe, is kind of in how you form mechanics to do something. And I still love electrical actuation. It's beautiful what we can do to control voltage on essentially the terminals of the motor and make it move the way we want it to. But to truly know how to convert torque into the desired motion, that's where kind of mechanics comes in. And we'll touch upon a few of these things. And I'll certainly highlight that making this do what you want it to do is incredibly valuable. It's very, in my opinion, very satisfying too. So we're going to do some Arduino stuff. What I have here is a Maker Wi-Fi 1010 board with what they call a motor shield on it. And so the motor shield means I have access to an H-bridge, which allows me to use pulse width modulation to adjust the voltages that are delivered to the motor. It also has terminals, things I can plug into to access the encoder. And the encoder will tell me the angle that we're gonna move at. Right. And so most of my seminars, let's see, am I sharing my screen? Okay. Yeah. Oh, I'm not sharing it on Zoom yet, though, right? So you ready for me to share on Zoom? Okay. Is that good? Cool. All right. Most of my seminars will start with something that looks like this. Yeah. And it's really, it's a robot that we used to carry around in a big trunk, and I'd fly all over the country and do a seminar based on this. All right. And the robot really doesn't do anything except move the way I want it to. It's not a robot that's really been assigned a task in this world other than just seminars. A little bit of an overstatement. But it reminds me, what are we really trying to do? All right. And I could probably talk for hours on all kinds of cool things. The basic idea is, look at that gray plate, doesn't exist in the real world. All right. But you know what's nice about that gray plate? I can move it up and down, I can rotate, I can make it do whatever I want it to do. Okay. Now, to make the robot really do that, it means controlling 6 motors that are going to essentially, deliver the angles that we're seeing in the linkage right there. And so the general idea, that's called inverse kinematics. Any mechanical engineers in here? Great. Okay. And inverse kinematics, you guys familiar with the concept? Not that we're going to go deep on it, right? But it's essentially how do I turn these motors to get the movement of the end piece to be where I want it to be. Again, very satisfying when you can get these things to work. And as we kind of went through this, I'll give you a little bit of a quick tour of Simulink. How many people here have used Simulink before? That's pretty good. All right, I'm very pleased to see that. All right, and let's see, I'm expecting now, based on what I just saw, that you've taken a dynamics class and that you've taken pricing controls, right? And so the feedback essentially is things like encoders, right, that go into this thing called a controller. If you're a hardware person, you think of a controller as an electronics board, printed circuit board with basically access, things you can plug into real systems. It becomes part of the overall machine. If you're a software person like me, or a simulation person, you generally think of it as an algorithm. And certainly the truth is, on a real electronics board with a good CPU, you put the algorithm that you design via simulation. And that's the general idea of what we're doing here. I'm going to go into the mechanics and electronics first. Now, those who have used Simulink before, they're often surprised by this. Okay, lines without arrows. Okay, now Simulink became famous because of this, lines with arrows. And it's the general idea of a mathematical calculation can be represented in a block diagram, and the arrows simply indicate the direction of how that calculation is proceeding. And it's certainly the perfect language for doing control algorithms with feedback, right? And so then we're going to go in here, and this is essentially the mechanics, right? And now here we're getting a little bit unconventional, right? Mathworks is restricted to a 2-dimensional canvas, and we got to make it happen in 2 dimensions. And generally what we're looking at here, you will see in tools like SolidWorks or Autodesk. What's one? What do you guys use here? SolidWorks, good. All right. Now I kind of picked a boring piece. We could go into that animation. I could show you exactly where that piece is. But it's a piece that's somewhat interesting because I'm seeing that it's connected to at least 3 things. All right. And I won't dive too much more into that, but I'll just say we're doing mechanics. If you look closely, you might have even noticed that there's a place to assign the mass of that part. Okay. Of course, it's a geometry created from SolidWorks, and therefore, knowing its shape, you know its volume. If you know the material it's made of, you know what its mass is. You also know what its inertia tensor is. You guys kind of thinking about, inertias we don't like to deal with because we have no intuition for it. Like I could pick up this laptop and tell you it probably weighs about 10 pounds, but I have no idea what its inertia is. Now, if I really did the math, I could probably come up with a base idea, but inertia is a tough one to deal with, right? So we love tools like SolidWorks that just give us a means to define the shape and do those calculations for us. There's absolutely like these kind of crazy conventions to one person's version of the inertia tensor is a little bit different than another's. And you better know that when you program it into a tool like what we're looking at now that predicts the mechanical motion. All right, anyways, my main point is to get to this Arduino. So I'm gonna just kind of go in here, and here you're seeing a much more recognizable description language for something physical, which is the electric circuit. And so we have a power supply here with plus minus terminals, which is feeding a network of DC motors. And we go in here and we see that. And here we get, I think, a general kind of concept of what we mean by the green lines, right? And so I'm gonna just zoom in here. And these are each of the motors. We got plus minus terminals right there. We have, of course, commands for what we want the motor to do. And then we essentially have something mechanical in its physical nature. That's the shaft. And then we have some redundancy in our robot, where the axle or the axis that's requiring the most torque is getting two motors driving. And just to take this just a little bit deeper, and I think again, we got good familiarity and experience with Simulink in the room. But again, I've been doing this for like 20 years, so there are probably a few things that are kind of familiar to me that may not be to everybody. Anybody ever use this block, the PID controller block? Did you use the automatic tuning? Did you? I didn't use it very well, though. Oh, okay. Okay. Well, basically what I'm showing you right now is kind of contained from, I'd say a seminar or webinar that I recorded and posted into a series of like 22 videos. On average, they're less than 10 minutes. So we'll make that available to you too, and you'll see some tuning of PIDs and that. And I love the fact that PID tuning exists, but I'd also say don't use it as a crutch, right? And again, the more you understand about this mechanism and the power electronics and motors are driving it, the more successful you will be at controlling it too. All right. I'd say that's probably far enough. I mean, I guess if we go even further, you'll see there is this thing that really is magnets and windings, and the windings are essentially going to carry current, which is controlled by the voltage that you apply to it. And that our means of doing that is what we call an H bridge. And so we're kind of seeing a representation of that right here, right? Now, you guys familiar with the term pulse width modulation? All right. It's the basic idea that there's no such thing as, a continuous dial that allows me to adjust voltage. If I have a 10 volt DC source, there's no way for me to actually directly convert that into, let's say, 7.3 volts, right? But what we do is we create something that really resembles that, and it's essentially turn it on for, let's say, if I got a duration, let's say, you guys familiar with this idea, duty cycle? Have you ever heard that? That we talk about, operating controls at rates, we'll say like 1,000 hertz. Motors quite often are like 10,000 hertz, which means that if I'm operating 10,000 hertz, it means I have the opportunity to change that voltage 10,000 times per second. And with computers, of course, we can do that, right? But what we're doing actually is way more complex than that, right? Because we're not really going to change it to 7.3 volts, for 1/10,000th of a second. What we're going to do is for that 1/10,000th of a second, we're going to hold for 73% of the time if my DC source is 10, and we're going to do what we call pulse width modulation, which is the average over that time. Okay. So anyways, hopefully that's not too boring or too, I'd say, off the point, but I want to kind of get that idea that the hardware level that you operate at really dictates so much of what you need to do to get these things to work, right? And if you're generating software that's going to do these beautifully clever things to make it move the way you want, you're going to still have to make it happen through these hardware devices like H-bridge and motors. All right, so if that's enough, I think I'll get into what I think we kind of advertise more, which is let's look at the Arduino. Now, has anybody worked with Arduinos? Okay. Now, have you worked with what's it called again? The Uno, but the essentially the Arduino programming environment. The IDE, yes, the IDE. Okay, and you've written like C code to kind of make it do some kind of cool things, and Arduino probably provides some pretty useful functions. Okay, so we're not replacing that. We're actually sitting on top of it. And think of what we're doing is going to essentially be like a graphical user interface to the IDE of Arduino. All right, and it means that kind of underlying everything I'm going to show is taking place because we have some really nice code generation capabilities. So let's go ahead and I'll shut this down. And let's get into this one. So let's get back into that directory. I'll have to put my glasses on. Okay, so let's kind of go for it here, right? Okay, so DC motor and feedback right here, PID controller, and then this piece right here, which, yeah, I use the term feed-forward controller. Anybody familiar with feed-forward, that term? Okay, how about feedback? PID is classic feedback. It's measuring it and using what you've been informed by through those sensors to do better, right? And so anyways, we're going to run this initially. I'll even show you what we're going to do. We're going to do a smooth transition that will start at, 1 second after, it starts calculating. And it'll take 3 seconds and it'll go essentially 4 rotations. And let's see. So I'm going to go to the Zoom meeting. I'm going to make sure that that shows up now. All right. I think so. I stopped sharing, right, Motaba? All right. And I'm going to move this a little bit right there. Okay. And maybe I'll move that like that, move this like that. Okay, and hit spacebar. Okay. It's not so bad, right? Okay. And what we have here is hardware. We need to connect so that it's going to run on the board. Okay. And it's going to run essentially this algorithm. We'll dive into it in a minute or so. Yeah, go ahead.
When you are plugging it into the computer and having that kind of read it, is there any type of special, toolbox you need to use in order to kind of
Sure.
start?
Great question. Thank you. So I'll begin, and it's more than what I'm going to show you, but I think what I'm going to show you will imply a little bit too of how we're doing this. So you'll see here the Simulink support package for the Arduino, and you'll see that I have the motor carrier right here. And the main things I'm using are the motor block right here and the encoder. And I just decided to read kind of the battery voltage as well. And I'll show you where they exist even. Right, so think of this as like my hardware interface even. Right, and you'll see that I'm sending in a voltage, but I'm multiplying it by 100 and dividing it by 11.1. Right, and so you'll kind of get the idea of this as you go into these blocks. And if you kind of read through the help, I think you're seeing enough right there actually to realize that if I send in 100, it's going to give me the full DC, source voltage. And if I send in a minus 100, turn it the other way, and it'll be a minus 11.1. And so then it's linearly scaled between. If I send in a 0, put in 0 voltage. Does that basically make sense?
Yeah.
Okay. But underlying all this is pulse width modulation and implemented through the IDE of Arduino. Right. But in the videos I produced, you'll kind of see me actually build this whole interface from a brand new Simulink model. So I think kind of step by step will be available for you if this is something that you'd be interested in trying out. And I absolutely
on the flyer, one of those links on the flyer.
Oh, I think it is on the flyer, isn't it? Yeah. So it's one of those what we call high spot pages. Okay. So let's go ahead and we'll try this out now. And I think I do need to make this bigger just so I get access to my monitor. I think either of these work. I don't really know why they have 2 of them, but let's just kind of go with it.
They only see the hardware.
Yeah. Well, the fact that it's kind of backed up with the videos, maybe that'll be helpful enough. But yeah, so I think you're correct. That would have been good. Okay, and what I like to show kind of as this is taking place, maybe I can move this out of the way right now. It's not exactly what I want to do. Okay, is I kind of show diagnostics what we're ultimately looking at here is all kinds of messages. They're kind of confirming that the code generation is proceeding properly. Okay, so what I mean by code generation, well, whatever that Simulink model is, it certainly represents an idea, an algorithm, a formulation of how the voltage is going to be changed based on kind of feedback conditions as well as what I'm commanding it to do. All right, and I already showed kind of what I commanded it to do, but they said go from 0 to 4 loops. There it goes right now. Did you see it? Well, I guess I have it blocked. I had it blocked. I'll do it again. Okay, perfect. Yeah, but I'm not doing it perfectly yet. So let me see if I can kind of do better on this next one. What I wanted to show though is first time through, we did pretty well, in my opinion. Okay. And I also want to kind of assert or at least confess the idea that what we asked you to do was super simple. Okay? It said, take your time, take 3 seconds to do 4 loops. And within kind of what this DC motor is and our ability to change voltage, that's not such a hard problem. That's why we do so well. Okay. So let me share my screen, make sure I get that comment kind of delivered properly. So let's go. And that's not the one, right? I want.
Yeah, that's the one. Yeah.
Okay.
Oh,
Yeah. Thank you. Okay. Okay. So those that are online, again, I'm going to assert we did pretty well. Not perfect. What's right there? You're seeing we're kind of missing. There's a Y. And up at the top, kind of settling in, takes a little bit to time to perfectly nail it. But again, I'll assert it's in my opinion, it's pretty good. Right. And the fact that it kind of starts out slowly might even kind of reveal a little bit of how we did this, which is that we did this with pure feedback. Notice this thing I call feed forward is multiplied by 0. So this is all done with the PID loop, right? And here's my issue with PIDs. By definition, they don't work unless there is a problem. We talk about it all the time. They operate on the error, okay? If there is no error, the PID will do nothing for you, okay? Now, don't take that as I don't believe in feedback. I think feedback's absolutely essential. But I just say, it's that idea that motivates me to do this in a little bit better way. And so what I'm going to do now, though, is I'm going to, here's the 3 pieces that really capture my attention. These 2 together essentially are the controller. Okay. This essentially is the device that will be controlled. It's our access to the motor. And then there's what do you want it to do? And that's our command signal. Right. And so let's make it do something a little bit harder this time. So we're going to make it 4 times faster. So I'm going to make that all happen in 3/4 of a second. All right. And so just again, before we get there, I'm reminding you how well we did before. All right. So let's do it again. And let's see what. So how do I get the image of the motor back up? I stop sharing. Okay. Well, we're gonna do probably another one.
You just want to show the
no, if you can get it, by all means. Oh, there you go. Perfect.
Relatively small, but this is.
Yeah, it's actually about to move, I think. Did it move? Oh, it already did move. Okay. All right. Please excuse our technical difficulties. All right. And here is essentially our tracking of that. And let's see. I move this out of the way. Let's move down here. Not so good, right? Not bad. Yeah. You try changing that voltage that rapidly. Okay. But so not so good. And if you measure that, I think it's about probably 70 or 80 degrees above. Okay, and so I'll use, this guy right here. And I can zoom like that. And you can see it should be at 1440, goes almost up to, I'd say 1510. So 70 degrees overshoot. Right. And takes, let's see, what's my timing? That must be like probably about 2 seconds to settle into kind of the closest. Yeah, go ahead.
Just to clarify my question, the green is the wanted voltage application, and the blue is what actually happened.
This is the language. I'll call that. That's my position command. So I told it, you know, take this shape. That's what I want to happen. And the blue is what happened, as reported by my encoder. Yeah. Thanks. All right. And it doesn't look so bad, but again, this is my job. I go and meet with all these companies in the Bay Area, and I show them how to do this. And I go, is that good enough for you? And if it's not, I go, okay, well, let's come up with some better ideas on how we can be even better. And some of my customers are operating at, we're 70 degrees overshoot. Their requirements are like less than 1/10 of a degree. Okay, so the precision at which people are operating at right now is, I believe, is very impressive. And the fact they're able to do it is really impressive. Okay, so I finally want to kind of go into this idea of feed forward. Right. Actually, let me explain what feed forward is. All right. Now, if you know it's a motor, okay, and if you know essentially the response to the motor, whatever that means, but there's something about that motor, there's a place you want to put it. Right. And when it comes to motors, and we have, how much time do we have? 30? Oh, okay. I might really get into this a little bit. Okay. But I want to kind of, DC motors were super attractive to me as a mechanical engineer because they had a description that was simple enough for me to understand, right? And it really comes down to, what is the electric circuit? And so that circuit, of course, has some resistance. It has a lot of windings, so it has inductance. And then there's kind of this configuration of the magnets with the permanent magnet that delivers this thing called the torque constant. Now, the torque constant, show of hands. You guys familiar with it all yet? Okay, I'll get into it a little bit. And what's interesting is you kind of get into electric motors. There's this idea that you don't get anything for free. And it kind of shocked me when I learned this. There's this thing that as the motor spins, that this voltage builds up. Okay, and they call it the back EMF voltage, and it's proportional to the rate at which it's spinning. Turns out that number is exactly the same thing as a torque constant. Now, torque constant simply says, I got so much current flowing through the circuit, my torques could be proportional to it. So that same K that multiplies I to get torque is the same K that multiplies omega, the shaft velocity, to get voltage. And I was blown away when I first saw it. And then somebody told me, well, it's really not that hard when you think of voltage times current is equal to torque times omega. And I'll kind of leave it at that for right now. So it's not as mysterious as you really kind of begin to think about the math. All right, but what I want to really talk about is if you know what those torque constants are, that can help you. Okay, and if you know what that mechanical load is, that can help you. And everything that you know about that system, in a way, I say you throw it into your feed forward controller. All right, and so I'll just kind of get into this to begin with. All right, that we have some sort of motion command. Now notice this motion command, I've labeled its units. All right, it's in degrees and we're going to express it in seconds. Now the other thing I have in here is I got a little indication to myself, position, velocity, and acceleration, PVA. All right, and here I just, anybody know what's under this block? Pi divided by 180. Okay, because we like doing cosines and radians for whatever reason. All right, there are lots of reasons we like radians, but anyways, you get into the appropriate form. And then you kind of get into this idea, well, what's the torque? Well, the torque that I need certainly is going to be the acceleration of the shaft times the shaft inertia. And then if there's some damping, well, the damping is going to oppose kind of the velocity. And so B times omega. And with that, based on what I wanted to do, I have a really good estimate of what the required torque will be. All right. Again, my information of what this is. I know the shaft inertia. I know the damping constant. I know it because I probably did tests. I know it because I trust perhaps the vendor that gave me the motor. So, all right. And then electrically, Yeah, and we could kind of get in it. I got like a PowerPoint slide I use quite a bit, but I'll kind of hit the space bar and make this big. Okay, if I know the torque I want and I divide it by this thing called the torque constant, well, I know the current, right? If I know current and I know resistance, which we typically do know, I know the component to the voltage to deal with I times R kind of voltage load, right? Now, the other thing is this thing called back EMF voltage. Well, that's that same K that I was telling you about, right? And so that K times the omega, because again, we know what we want it to do, you know? So if we do this really well, we're going to go into this knowing the angular velocity, right? And so I take that omega times K, and I just add these two up, and that's what I'd call the feed forward voltage calculation, right? So it's your knowledge of what this DC motor is. All right, and anyways, I'm going to turn this on this time and just remind you, we had about 70-degree overshoot last time. And I'll again hit monitor and tune. And so let's see how we're doing this time. So that's the motor right there. I'm not sure if you see my little piece of tape that's on there, but hopefully we'll see a little bit of indication. And we're seeing it progress, through the code generation down here. And I'm looking for it when it says successful build, and then I know it's going to start moving pretty quickly after that. And the whole thing takes about 30 seconds, right? And you know, the basic idea is this idea of an algorithm was kind of captured without getting into the specific, you know, am I representing this signal with 8 bits or, you know, 32, and is it, you know, expressing with a decimal point, all that kind of stuff. You know, I don't need to think about that yet. There it goes, right? And, you know, and ultimately to be on that embedded processor provided by Arduino, you know, it doesn't run Windows, it doesn't run, therefore, MATLAB. You know, your means of getting what your idea is through code generation. All right, and so there we are right now. Isn't that cool? When I first did this, you know, I bought that, tried it out, and I tried out this idea, and I saw like whatever, probably like 60 or 70% reduction of overshoot. I was like, that's the coolest thing. And in general, I get that kind of, you know, rush or charge from kind of going to hardware and making hardware do something from what you're doing on your laptop. It's really cool. So,
we have time, maybe I can translate what you just mentioned, which was excellent, in terms of 3 courses that students are taking.
Okay, yeah, please do.
It'll take maybe 2 minutes.
Yep.
So what it was done here, it was an excellent example of what you will see in these 3 courses. So on the microcontroller that we just had, we are using a similar microcontroller to what's being used here. So this is the microcontroller we are using. We are using the IoT. And what he did, he ran the program on the microcontroller, not on his computer. So what you're seeing here being done, it's basically, this is the computer, and the Simulink right now here is the interface, right? So this is what we are doing, what Terry just did. And so this is the microcontroller part. So it's the hardware sort of program being run on the microcontroller, similar to what you do in microcontroller class. He also talked about, you know, the torque, omega multiply T, being the equivalent to the electrical side. So this is related to the 305, 307. Then you're talking about the modeling. This is a coupled system. So it's an electromechanical system, electromechanic, and we have magnetic system too. So it's a coupled system that we have electrical world, we have the mechanical, and they are basically making those ODEs. And this Simulink is actually solving these ODEs for us. So what he showed us on the Simulink, this is part of those ODEs that's being solved. We put that on the hardware and we execute that. And regarding the control, we also saw 2 things. We saw the PID controller. Was it PID or it was just?
Oh, it is a PID.
The whole PID. So we are going to learn that at the end of the class. So for those of you 447, we are going to learn the PID controller at the end. And we also talked about the feed forward. This is another type of the control that, as you can see, it's going to improve, you know, the performance or the response of the system. So it was the combination of all of these 3.
at the same place, okay?
Yeah, and I like opening up with that robot just to kind of show where you can end up with it. And trust me, all those same basic pieces are in that model, including what is a much tougher calculation when it comes to the mechanics of a robot, right? But that's what tools like SimScape Multibody have been developed to do. And it's this idea that I can tell it how I want it to move, and it's going to tell me what the torque of each of those motors need to be. And there's lots of kind of really kind of cool things about that that I'd probably get into if we were talking like 3 or 4 hours. But that was the point of creating the videos too. And the videos are available through the PDF. I think my email address might be available through the PDF. If it's not, please send it to everybody. And I certainly encourage you, send me emails. And
If you could write on the board, it would be great.
sure. This is one of those indelible, never erase things. Right?
No.
Okay, so yeah, so T Henry.
So this is a generous offer to use it if, so he's willing to help you. And if this is, appreciate it. And I put that in the chat box.
Yeah. Yeah. Let's see how much we got. Maybe like 20 minutes left, something like that.
Yes.
Okay. So so I kind of went through like the early parts of Simulink, which maybe you guys already have, but I kind of like getting into it a little bit. And I could go into let's see how you use Simulink. But I'm also, you guys got questions, I'm happy to just kind of focus on what you want to talk about too. But if not, let's kind of get into this. Let's see. So how do I get access to? I think if I know. Well, here's my Simulink browser. So let's go here. And I did have a PowerPoint slide. I usually don't like to use PowerPoint that much, but I think this is a good one to. I'm still sharing, right, Matama? Okay. So I think that this isn't over. It's not over, but any of this looks a little bit. Yeah, I've been looking at this for 20 years. So again, it all looks like obvious to me. But there's essentially Kirchhoff and the key kind of, I'd say, origins of how you need to consider a DC motor. Kirchhoff's really great for circuits. And we got a general description of the circuit right here. The DC motors are kind of represented by their inductance and their resistance, but they got this magic thing, that if I put current through the wires and basically how those windings have been aligned with a permanent magnet, they generate torque, and we quantify that with torque constant, right? But with that being said, and then we get that backing up, the voltage balance is inductive voltage drop, resistive voltage drop, and backing up, right? Mechanically, it's rotational, so it's not as easy as F equals MA, but it's you apply torques and things will rotate. And we'll measure that rotation by the angular acceleration. So our key variable is omega, the shaft velocity. And so if it's okay, I'm going to just kind of jump in and do that demo. All right. And so let's get up here, get a Simulink model. We'll bring in the browser, pop it out. So it'll be nice and big for me. Like that. Okay, so let's go grab some blocks. And I definitely want an integrator. And I want a scope so I can look at things. And I want a gain block so I can set some parameters. And let's see, I want a constant. And then there's one more that I use at a very high rate, and that will be my addition block. I probably use multiplications quite a bit too, but let's kind of get the basics down on this. And so what I'm going to do is set up my initial demo, right? These blocks are just hang out, and I could do anything. So I hit run, and I'm doing something that nobody would ever do, which is I'm sending a constant into a scope. So this is how I started out this demo 12 years ago, it was a little more impressive because I'd see a horizontal line. But our developers were like, well, we want to optimize and be efficient. And go, well, you're sending me a constant. I only need to make that one calculation. So they give me a data point even. All right. So for them to do more work than that, you have to give them something a little meatier than sending in a constant. All right. So I'm going to now send in a constant that will be integrated with respect to time. Anybody want to guess what we're going to see? Yeah, and what's it going to look like?
It's going to be going from 0.
And we're going to run it for 10 seconds. And beautiful. Yes, absolutely. That's what we got. All right. And so let's go and I'll get rid of the marker. And we'll just deal with lines now. Okay. All right. So the next thing I want to do is, okay, and I'm going to put in a 2 right here. Okay. Now I'm not sure if you guys are familiar with my notation I'm using, but the triangle. What do you expect this time? So it went from 0 to 10 in 10 seconds. Okay, so that 2 is a multiplier, right? And so now we'll get to 20. And I can hit the run button right there. And it looks the same because it auto scaled me. And so it looks like the same one, but now we get to 20. Right? Okay, now I want to drag this guy right there. Show of hands, or anybody want to comment? We're solving a set. Go ahead. Yeah, absolutely. So you can kind of go up like that, sort of like a parabola. Okay, so it seems very academic what we're doing, but if you start thinking of the idea that since we're going to get into rotational motion, I'm going to call this 1 divided by j. Okay. All right. And so that's essentially 1 over my inertia. And if this is my torque, then I've essentially just gotten the angular acceleration, which I'll just call d omega dt. All right. If I send d omega dt into an integrator, got omega. All right. And if I integrate angular velocity, what am I going to get? Angle. Right. And at this point, you might start paying attention to some things I'm just kind of casually passing over quickly, like initial conditions. Right? And of course, they're really important. They're even more important when you do the kinds of things that we're talking about. You know what the hardest part of electromechanical systems is? If you're good in a domain, let's say like mechanics, you totally know, oh yeah, I need to set initial conditions on angle or shaft position or whatever. And you kind of forget, oh, electrically there's initial conditions too. And so the idea of, and we'll kind of see that as we move into electrical, which we need to because we're doing a DC motor. So anyways, but let's kind of work with this right now. All right, and I'm going to take this, drag it down right here, right? And I'm going to put this in here. And the basic idea of what I want to do next is I want to account for some damping. All right. And damping is proportional to shaft velocity, right? Which is what I have here. And so then to really get this right, I need to get that proportionality constant.
This is what we were doing 2 sessions ago in control. So he's building those.
Yep. Yeah, and so we call B usually for damping, so I'll put that there. And now I want to get electrical on you, and so instead of being 1 over J, I'll make it 1 over L, and then all of a sudden it's di dt. You guys with me on that? So what we're really kind of getting at is what's the voltage carried by that inductor, all right? And since there's kind of inductance in the circuit, there's resistance in the circuit, and then there's this back EMF piece, really narrowing it down to what the inductor is going to carry requires a little bit more math too. And so I'm going to kind of get at that right now. All right. All right, so this little add block. I'm going to do it this way. I'm going to be a little old school on you here. All right, and so the list of signs, which define the ports coming in, I'm going to make it minus, plus, minus. All right, and The plus is for my applied voltage, when I'm gonna let this constant to do. But again, I gotta kind of, ooh, I did this wrong, didn't I? No, there it is. All right, I just need to relabel this. Right, so that's I now. And so what the inductor is gonna carry on voltage is gonna be affected by how much resistance is in the circuit. And so we can turn that off and we'll call that R. Okay. See, that doesn't like that I just created a variable and didn't tell it what it is. It says glowing in pink now. That's, or it's mad at me. Yeah, that's what the red indicates. All right, and so then finally, let's kind of get the mechanics and the electrical connected. All right, and it's hard to do Zoom meetings, you know that? All right, and so we're gonna bring that in. All right, and what's our constant? Okay, so this is the DAC EMF voltage. And think maybe I can make this smaller and then we'll get it unblocked by these various screens that are in the way. And I hit the space bar and that resizes it. Is that big enough? You guys seeing that okay? All right, and I guess a couple of things. That's interesting, I got a B in there already. And that's because, you know, how does it know what B is? Because in my previous demo had B. Right, and so let's just kind of go in here. You guys familiar with kind of the basics of MATLAB where we got this thing called the workspace over here? Right, and so I'm going to kind of clear my workspace. So it's completely empty now. And if we went back, it wouldn't even like my B. But let's go and generally fix this overall thing. And I like going to my command history. Everything I've ever typed in here is available. And I'm going to look for an R equals, and you can see R equals 1, J equals 1, B equals 1, L. All right. So I'm totally being a theorist and essentially saying data doesn't matter. All right. But we're going to get the formulation correct through this. And with that, and if I hit a Control D, it will update the chart and all those things are good now. And so we're real close, right? So we got, this is now called K. All right, and so we have B for damping, K for back EMF velocity. And let's get rid of, okay, if I integrated current, what would this be? Be charge. Means I could have a battery in there if I want, but I don't care, so I'm gonna take that out. And then I'm gonna just take a little bit of current, put that in. And let's put this in as 1 divided by J. Okay. And this will be equal to B. The block was called B, the variable was not called B. All right, and finally, this needs a multiplication of that same K. And I think that'll work. And we'll hit run. And that's what our current would look like. And this is what our shot velocity would look like. Okay. And we have 5 minutes.
Yes.
Okay, so let's do one last thing. All right, and let's put a controller on. Create a subsystem. So essentially all that was put in this one box. We will label things now and we'll say voltage is in, current is already labeled, and omega is already labeled. Okay, so that's what's inside this box here, and that's our DC motor. Okay, and then finally, let's put a PID in. And like, do you guys want to control velocity or you want to control position? That's easy. You sure you don't want position? Okay. All right. So how am I going to get position? I'm going to put an integrator in. And again, I might choose to come up with a real initial condition, but 0 can be real as well. And so we'll just kind of go with 0. All right. So position has been identified. And let's see, we're doing things in radians. That's kind of the natural thing that will fall out of this type of formulation. And so I don't know, let's go for pi. Right, so that's essentially 180 degrees is what we're shooting for. Okay, and now I'm going to type in SUM for sum. We're going to make it look like a real feedback loop, right? And that what this is really going to be is going to be the difference between what I want it to be and what it is, right? And so therefore it can't be plus plus, but the one coming in on the bottom, and that's very much a notation thing, but I think a good one, all right, that kind of configures the operation of the PID, all right? So the terminology we use is that you use feedback controls to eliminate error, right? And they do, again, nothing if there is no error, all right? So it sends in a 0, give you a 0, right? But anyways, we got a PID. Now, there's this whole like S, you guys know what the S is there for? Yeah, I didn't. Yeah. Exactly. So Laplace transform. And controls engineers love Laplace generally, all right? And it means that they turn hard differential equations into algebra almost. It's a super clever idea. And essentially, that error will be multiplied by a proportional gain defined there. We're going to integrate that error. It's a really kind of cool idea of if there's, kind of this error, like if I had gravity acting on this thing, it's this integral term that would detect that there's something systematic that's leading to an error. So, and it's the hardest one to explain. But then the derivative, which is a lot more like damping, basically will kind of modulate your overshoot if you do overshoot. The general idea of proportional and derivative is like a spring damper. If I put in something like this, Kp would map to like a spring constant, D would be sort of like the damping constant. Okay, but again, we're going with default values. We'll see the numerical derivative being performed for us, which you always have to use. And there's something essentially, I'd just say, think of this as we call it a filter coefficient. And there are 4 parameters that are essentially defining this algorithm that we're expressing pretty cleanly right there. Right, so we chose to throw in this additional integrator so we get position. So this is what's being controlled. And so we're now telling it to go to pi, right? And that kind of looks like a spring damper, doesn't it? So the last piece to this is what they call the tuning of the controller, right? And so feedback is absolutely informed by the device itself. But I just say that again, it's sort of indirect how it's essentially tuned to deal with the natural dynamics of that device to essentially adjust and eliminate the error. And that's why you learn about Laplace transforms and you learn about frequency domain and all that sort of thing. But what I want to get to is, here's my tune button. So, okay, am I being crazy? I'm not even seeing it right now. Oh, I'm using a different kind of PID. Let me try that again. So let's get a Simulink. Continuous. PIDS controller. Okay, all right, and so let's hit tune. Where's my apply button now? Sorry for these kind of difficulties I'm having with the Zoom meeting. I'll try to practice for this kind of thing in the future. But
This is understanding.
an external, internal. You can see them there underneath here. Oops. Okay. So let's click on tune. Apply changes. So let's hit the apply button. Well, I didn't realize they changed it so much in the 22B release. I'd say we're not far from it, but I also want to, let's see, update to PID. One thing. I want to just kind of, I think I'll move on from that, but are you trying it right now?
It's just genuinely possible.
Okay.
I see this one.
Okay. So I'm going to update the PID block. What I'm kind of disappointed in is I kind of like the images that it produces. It does this normally, and you'll see these in the videos. And I'd imagine it's available still, but there's some sort of update in the tool that we put in. But what I want to do is just kind of update the PID block, because we certainly know the last time we ran this, we had a problem, which it was just kind of oscillating like crazy. All right, and so let's hit close. And let's run the whole thing again, because that reflects some of the, see, I'm not crazy about that. So I'll figure it out. But what I will kind of endorse is take a look at the videos. There's some PID tuning that I do in some of the videos. And this will be much more kind of, I'd say, helpful to you, what you'll see there. But sorry about that issue.
It's getting there, but you need more time. So it's being simulated on just 10 seconds. If you simulate a little bit longer,
Now let's do that. Just to, again, we'll run it for 100 seconds this time. And what we do, we did pi over, or we did pi. Yeah. And so you can see it's going to 3. And yeah, absolutely, it'll settle in there. But again, I'm a little aggravated right now, right? So my aggravation is it's way better than that. Okay, and it's this idea that you enter in your own kind of requirements and you say I want it to be a little faster than that. It'll kind of recalculate it for you based on what's a better design for you. So, anyways, I'll practice it. Perhaps I'll come up with some other
you're going to see that in the control class at the end. You're going to work with PID,
Okay.
the 2 bars on the simulating, and you will see that.
Okay.
You're going to model this in the control line. The whole motor, but that was an excellent introduction.
Okay, well, thank you. And I love coming up here. So if you want me to come up, then I'd be happy to. I live about 25 miles from here. So.
Excellent. Thank you so much. So let's thank our presenters.